In this video, we'll talk about inflection points, what they are, and how we can find them using calculus. So an inflection point sort of fills the role of a critical point for the second derivative. Except we're a little more particular about when we actually have an inflection point on a curve. And our main criteria is that inflection points only happen when the curve actually switches concavity at that point. So it goes from either concave up to concave down, or concave down to concave up. If the function has the same concavity through the point, then it's not an inflection point. So our definition here is the following. We have a point C f of c on the graph of the curve. This is an inflection point if that point on the graph has a tangent line, by that I mean f prime of c exists, and the concavity switches sign across c. How do we go about finding these? Well, the logic here is the same as how we found critical points. If concavity is going to change sign at the point C, it means that either f double prime of c is 0 because I'm going from negative to positive crossing through 0 at that point, or f double prime doesn't exist and I'm getting some weird jump or asymptote going on at that point. So at inflection points, we have to have that either f double prime is 0 or it doesn't exist. That doesn't mean that all points of this form are inflection points, but I can put together a list of these points, and those are all of my possible inflection points, and I have to check to make sure that the curve actually switches concavity at those points. As an example here, let's find all inflection points of the function x minus 2 times 1 minus x cubed. We analyzed this curve before, right? Our function, if we expand it out, and then we could take our two derivatives just like we did in the previous example. If we look at this set here, we see that this function, its derivative and second derivative all exist everywhere, which means I always have a tangent line, which means there's no weird points where it doesn't exist to make me not have inflection points. So then find inflection points, I want to draw the number line for f double prime that we had before, which we know had the following form. Now, I'm looking for points where f double prime either 0 doesn't exist, gives me two options, gives me 0 and 1. Now I want to determine if these are actually inflection points. And the criteria that I have left is, does the concavity change sign across those points? And in both cases, the answer is yes, right? At 0, we're going from negative on this side over to positive on this side, so that changes sign. And at 1, we're going from positive over to negative, so that changes sign. Therefore, both of these are inflection points. So my function f of x has inflection points at 0 and 1. And if you want to find the actual points in the graph, you can plug these back into the function f at the beginning. And these points occur at 0, minus 2, and at 1, 0. So that's the inflection points and how you can find them using the second derivative to determine where the concavity actually changes sign for this function.